Today we will be solving radical equations. In case you've forgotten, radical is the name for this symbol right here. So we're mostly going to be doing square root equations, although I will show you how to do equations where it's not a square root, but like a cube root or whatever root you end up with. We're going to start with a single radical like this equation right here. When we get done, I'm going to need to talk about extraneous solutions, which is a new thing. Based on how we solve these equations, sometimes you get solutions that don't actually work. I'll explain what that looks like. Radical on both sides, right? This one only has one radical. As we move through, we'll have radicals on both sides. When it's just the radicals, it's actually a little easier uh, than other ones. But when you get two radicals plus extra stuff, things get a little messy. It's not so bad, but it's definitely more work. So I'm going to show you one of those as well, and then you can get started on your homework, classwork, or whatever we're going to call it. So as far as solving an equation with a single radical, we use basically in algebra 2 for the rest of algebra 2. Our basic methodology is going to be to figure out to find the parent function or the basic function we're using here and get it by itself first, and then we're going to cancel it out. So right now the radical is sort of our parent function here, and this -1 is making this side more complicated. So we're going to get the square root all by itself. So that's our first step, is to isolate the radical. So we're going to add the 1 to the other side, which gives us the square root of x plus 2 equals 6. Now we've got the radical all by itself. Now we're going to cancel out the radical. The opposite of a square root is squaring. So we're going to do that to both sides. We're going to square the left side. We're going to square the right side, which is going to cancel the radical. So we just have x plus 2 over here because it's canceled. And over on the other side, we're going to get 36 because that's 6 squared. Right, so then I have x plus 2 equals 36. Just subtract 2 from both sides, and I'm going to get 34. It's a good idea anytime you do radical equations to check your answers. When your equation solving process involves squaring both sides, it's really important you check your solutions, because sometimes it will appear that you have solutions and they won't actually work. This one does work. When I stick 34 in here, I get 34 plus 2, which is 36. The square root of 36 is 6, and 6 minus 1 is 5. But that won't always be the case with radical equations. This one here looks very similar to the one we started with, but it actually won't work out. So when I solve this one, first I'm going to subtract this 5 over, and I get square root of x plus 2 equals -4. And then when I square both sides, I'll get x plus 2 equals 16. So I square both sides. I get x plus 2 equals 16, which means x is going to be 14. When I try to stick that in, I'm going to get the square root of 16 plus 5 equals 1, which actually doesn't work because that's 5. That's actually 9. My 5 got all messy. That's actually 9 equals 1, which is definitely not true. Now what happened here is we needed a -4. When I squared both sides, that -4 turned into a positive number, which isn't always bad. Sometimes that works out, but sometimes that makes a solution where if I could get a -4 out of here, this would work. But there's no way to get a negative out of a square root. I should say there's no way to get a negative real number out of a square root. So this equation actually has no solution, because if there were a solution, it would be 14, but 14 doesn't work. So when you square both sides, it will give you all of the solutions that do work, but it may also give you some that don't work. Some of your equations will have multiple solutions. You may have a quadratic when you get here, so you'll have 2 or more solutions, and some of them might work and some of them not work. So you have to check every solution. If none of your solutions actually work, you have no solution. Just cross out the ones that don't work. They're called extraneous. Extraneous. And up until now, you haven't seen any of these. But as we move along in Algebra 2, some of our advanced techniques, like squaring on both sides, can produce solutions that look like they might work, but don't actually work in the original equation. And we're going to see that more and more as we move into the end of Algebra 2. As my next example, this one, it's basically the same as we've already seen. The biggest difference now is a cube root instead of a square root. It doesn't matter what the index is. Like it doesn't matter whether it's a cube root or a fourth root or a seventh root. The process is the same. I'm also going to point out that this is the radical notation. If you have a fractional or rational power, that means the same thing. The cube root is the same as the 1/3 power. So if you see a situation that looks like this, the solution method is going to be the same as this. The radicals and the fraction powers, they're the same. So the first thing to do is to isolate it. So I'm going to add the 4 to the other side. Oh, I guess I'm switching to the rational exponent notation. It doesn't really matter, though. I could just as easily have stuck with this one. It means the same thing. Now I'm going to divide 2. Now here, because it's not a square root, it's a cube root. To cancel it out, I have to do the opposite of this. So if you've written it as a fraction, you use the reciprocal power. So 3/1 is the power I want. If you stuck with the radical notation, it's just a matter of remembering the opposite of a cube root is cubing. So 3rd power on both sides. 2 to the 3rd power is 8. And these just cancel, leaving 6x minus 3. The whole point is that those cancel. So you don't need to, square or cube root the 6x minus 3. It's just what's left when the cube root cancels with the cube. Now I've got to add 3. 6x equals 11. So x equals 11/6, which is, well, I mean, it's the right answer. It seems a bit unfortunate. When you cube both sides, you don't produce extraneous solutions. But you can always check this. 6 times 11/6 is 11. 11 minus 3 is 8. Cube root of 8 is 2. 2 times 2 is 4. 4 minus 4 is 0. So this solution definitely works. But like I said, cubing both sides doesn't change the signs, so it doesn't produce extraneous solutions. All right, as promised, now we're going to look at what happens when you have a square root on both sides. Now, if all you have are a square root and a square root, it's actually even easier than the one we started with, because when you square this side to get rid of that square root, you're going to square the other side to get rid of its square root, and the square roots are just going to each cancel. And so you can set the insides equal to each other. I am going to point out to you again, this is squaring both sides. You can sometimes solve this equation and get things that don't work. So when I'm going to finish solving this, I'm going to subtract x from both sides. I'm going to add 1, which gives me 4. X equals 4. So I need to check that. In this case, we're looking at the square root of 7 equals 8 minus 1 is the square root of 7. And the square root of 7 equals the square root of 7. So this solution works. It's not extraneous. But that's not always the case. Make sure you check to make sure they're not extraneous anytime you do this. Just occurred to me that I need to prepare you for something that may not have been in one of my examples. Oh, no, not this year, next year. Okay. So now we have number 4. These ones are definitely the most work. We have 2 different radical signs in our equation, but we also have stuff that's not in the radical sign. So our initial approach is going to be the same. We're going to isolate one of the radicals, and we're going to cancel it out by squaring. In this case, we're going to square both sides. The problem is when we square both sides, this one's not going to square cleanly because we can't just square the one part. We have to square the whole thing, and you can't distribute powers over addition. So in this case, we're going to have to FOIL this times itself. It's going to get kind of messy. We have to FOIL it by itself. So the squares don't just cancel the square root here because of this plus 3. Now the left side works out nicely. because it's just the square root. So the square and the square root cancel, we get x plus 1. But on this side, we're going to have to remember to FOIL this. I normally don't write this out because I remember my binomial square pattern. So if you do, remember you can square this and then multiply them and multiply by 2 and square this. It's much faster. But just in case you don't want to remember that, I'm going to FOIL these the long way, just because that's what you can fall back on. Now when I do FOIL, I'm going to multiply the first two together. This is the square root times itself. That's the square root of x minus 2 squared, which is going to cancel. So in the first bit, we do actually get a nice clean square. The square cancels the square root. Everything's going okay. But when I do the outside 2, I'm going to get 3 times the square root of x minus 2. The square root didn't go away. On the inside 2, 3 times the square root of x minus 2. It's the same because it's the same thing, right? And then plus 9. So I've got 6 square roots of x minus 2. These are the same. I can add them together. 6 square roots of x plus minus 2 and 9 equals x plus 1. So I squared both sides here, and what I have left still has a square root in it, which is unfortunate. But the good news is it's only got the one square root in it. So now I can finish by getting this square root all by itself and squaring both sides again. So it's more work because you end up having to square both sides twice, but it's not anything new. It's just more of the same. So I'm going to combine like terms. The -2 and the 9 are going to combine to make 7. And I've got 6 square roots of x minus 2. So I'm isolating this square root. I got to subtract the x, which is actually going to cancel. And I'm going to subtract 7, which gives me -6 equals 6 square roots of x minus 2. Divide that 6, I get -1 equals the square root of x minus 2. Now I've isolated my square root again, so I'm going to square both sides. And I get 1 equals x minus 2, which means x equals 3. Don't forget to check for extraneous solutions. In this case, I squared not just once, but twice. So it's, excuse me, it's very possible to get an extraneous solution. I'm going to check it then. My original was x plus 1, square root of x plus 1 equals the square root of x minus 2 plus 3. So if I stick in 3, I get the square root of 4 equals the square root of 1 plus 3. So that's 2 equals 1 plus 3, which does not work. It's extraneous. So this is not a solution. There's no solution to this one. And that's going to happen sometimes. So you should be prepared. Sometimes it'll work out, sometimes it won't. And you can't really tell until after you've done it. This should be enough to get started. If you need to watch these examples again, that's fine. And as always, you can contact me if you have questions.